Hi. This talk is about work I did together with Daniel Escudero and Nikolai Volgushev on securely training decision trees with continuous attributes. So a decision tree is a very simple predictive model. Say I want to predict whether it's going to rain tomorrow, then my model could be as follows. I look at the temperature today. If it's more than 20 degrees, I say it's not going to rain tomorrow. If it is less than 20 degrees, I look at the rainfall today, and if it's more than 2 millimeters, I say it's going to rain tomorrow, and otherwise I say it's not going to rain tomorrow. Now, to come up with this model, I could, for example, for 1 month, keep track of rainfall, temperature, and look whether it's going to rain the next day, feed this into a training algorithm, and the training algorithm might come up with this model as sort of like the best decision tree that matches the data. Using this decision tree, I can then predict outcomes on new data. So here in this talk, we are looking at securely training decision trees, where the training data is sort of like owned collectively by a set of parties. They each own a part of the training data, but they do not want to share this training data with each other, but they are all interested in the output model. So ideally, they would have this magic box. They send their part of the data to this magic box. The box computes the decision tree and then outputs the decision tree to all of the parties. So when I say they jointly have the data, what could that mean? For example, we have this table. Each party might own a different set of records in this tree. Then we'd say it's horizontally partitioned. Vertically partitioned is when the parties have access to each to some attributes, but for all of the records. Our approach is more general, so we assume the input data and the output data are secret shared, which means that basically any composition of this table can occur for the input data. One party might just have one cell, or the table might be the result of some earlier secure computation. So we use multi-party computation, which is a technique that allows us to evaluate any function securely, and it offers an absolute privacy guarantee within the security assumptions. The security assumptions might be that no two of the parties collude with each other and share their data. So with MPC, the parties are able to sort of like emulate this magic box that computes any function by running a protocol among the parties. This absolute privacy guarantee of MPC is a contrast to, for example, federated learning or differential privacy, where usually there's some bound on the privacy, but there is always some information being leaked. In MPC, the only information that is being leaked is the output data. We use generic primitives, so we build on top of a generic MPC protocol that just implements secret sharing, which is a sort of encryption of values where each party gets its share of the value, and they have protocols for computing sums and products of these encrypted values. Also very important for decision trees is secure comparisons. So we have two values and we want to learn a bit to learn whether the second value is less than or equal to the first value. Because that's the main primitive that we are going to be using. So we can evaluate any function using MPC, but there's a large overhead. So if an algorithm takes 1 second to run on your local machine in the clear, then using MPC, the same protocol might take days. So there's a big incentive to develop efficient algorithms because the running costs overhead are large. So we developed a secure algorithm for training a decision tree, and we wondered, is this good enough, basically? Do we get an acceptable running cost and time, and then the resulting model, is it going to be similar to in the clear learning methods? And as we shall see later in this talk, we found the answer to be yes. Most prior work on decision trees in MPC focuses on secure evaluation. So say we have two parties, one of them has a model, the other has a sample, and it wants to sort of feed the sample through the model without the party that owns the model to learn anything about the data or the output. But here we focus on actually constructing this decision tree. So there has been prior work on this, which was a secure version of ID3, which is limited to discrete attributes. So we only have, say, binary or attributes with a few possible set of values. This allows for a very efficient algorithm. but in practice, we often have continuous attributes. So we are interested in this. So in the clear algorithms for this are usually called C4.5 or CART, and we have a sort of very stripped down version of this that we're going to develop into a secure algorithm. So this basic stripped down algorithm looks like this. For each attribute, we're going to consider all of the values as potential splitting points. So we take an attribute, we take the first value, and then we're going to consider which rows have value temperature less than or equal to 19.1 degrees. Now in this case, we have 4 rows. And then we're going to look at the corresponding outcomes. Ideally, we want all yeses or all nos. But this doesn't happen, or this doesn't usually happen. So we measure how good this splitting point is. And we measure this with the Gini impurity. So for each of the values that we have, we're going to take the weighted average of the Gini impurity on the left of the split and the rows on the right of the split. So on the left, we have these 4 rows. We see the fraction is 1/2, so the Gini impurity will be 1/2. And we weight this with 4 rows. And on the other side, we have 1 row with perfect split because we only have 1 value. And so the algorithm proceeds as follows. For all attributes, for all splitting values, calculate this weighted Gini value and then minimize it. Then output the node that the attribute and the splitting value that minimizes this. Now the downside of this is that it requires a lot of secure comparisons per node, and this is very expensive in MPC. So in our secure algorithm, we're first going to sort based on each attribute. For this, we use a sorting network. Sorting network looks like this, for example. For 4 values, we have this sorting network. We go from left to right. We have this value that we feed into it. So these bars indicate comparator gates. So here we compare whether y3 is less than, or say less than y1. This is true. So we swap these 2 values. So y3 goes to the first position, and then we keep on going. So y3, here we swap again, and here we swap again. So y3 is going to end up in the 3rd position. Now the nice thing, so the constructions for this sorting network, like an odd-even merge sort, exist with log square n depth. The nice thing and why we use a sorting network is because we can evaluate this sorting network once, and if we record these the results of these comparisons, then we can feed other vectors into this sorting network, and then get the this allows us to store and apply this sorting permutation. So in our secure algorithm, we're first going to sort on each attribute. Now, for now, just assume distinct values. In the next slide, we're tackling duplicate values, because this is an additional difficulty. So, and then for each node in a tree, we're going to keep track of the active samples. So for the root node, we are considering all rows, but after the root node, we're going to split into the left branch and the right branch. And for the left branch, we're only considering a subset of the rows. And because we're doing this obliviously, we cannot just reduce the number of rows, but we're going to select based on oblivious bits whether we take the row into account or not. So we have the secret shared indicator vector with binary values that we call active samples to indicate whether we take the row into account or not. So if we have this table, then we're going to sort based on an attribute. And then we're going to consider first the first row as a splitting point, and then the second row, etc. And then because we have sorted already, so we're also applying we've also applied the sorting permutation to the outcome column, and then we only need to count the number of yeses here to get this this weighted average Gini value. So we're going to do this for each row. And if the active column is 0, then we just disregard the Gini value that we calculate. And then we take again the best possible attribute and value. So we need to apply this permutation for every node. So this also becomes a bit expensive because the sorting network requires n log square n of these swaps. And to optimize this, we actually convert this into a permutation network, which we have of smaller size. Now, to handle duplicate values, basically, we're going to check whether the next row has a different value. If so, we take the row into account, and otherwise not. So the first row, yeah, this is valid, this is valid. But here we have a row where we have an identical value. And this means that this splitting point, we can never get it, because if we say temperature less than or equal to 12.4 degrees, then it will always take both of these rows into account. So this is not a valid splitting point. So this is why we have this check. We keep on going through the table, but we see this causes a problem here, because here the next value is the same, but it's not active. So we need to take into account only the active rows when considering these neighbors. And this becomes a problem because we don't know how many non-active rows there are. So our solution is basically to copy the rows that have active values over preceding inactive values. And this, with this, we have a solution that does this in log n depth. So we basically per node we only have this log n depth factor, which greatly improves the efficiency of our method. So for the basically we implemented our protocol using the MP Speeds framework, which offers a whole bunch of basic so these MPC primitives, different MPC protocols, and we use computations in the ring, so modulo 2 to the 64, which suffices when n is less than or equal to 2 to the 13. We used 3 parties with tolerating 1 corruption, so we want no 2 parties to collude, based on replicated secret sharing, which is very fast, especially in CPUs. So for passive security, we have these cheap dot products at the cost of 1 multiplication, which we use often when we count these number of yes and no values in the outcome column. Then we ran benchmarks on the Amazon cloud, and we use the running times for these. So we have this, as I mentioned at the start, we have this use case. So we've sort of validated whether we can achieve comparable accuracy and in an acceptable running time with our protocol to state-of-the-art in the clear method. So we have this real-world data set which has almost 300,000 records and 128 attributes. And so the goal of this original analysis was to predict the risk of hospital transport of elderly patients in the next 30 days. This was obtained through some personal emergency response system that the patients had. And initially, this data was trained using extreme gradient boosting trees. So the advantage of decision trees is because they're quite simple in nature. They work well with these aggregation methods like gradient boosting. And then the idea is to combine a lot of trees that are trained on subsets of the data to have one large model, which performs sometimes similarly to neural network-based approaches. So here the study was done using just in the clear data, but we were told that this there is a privacy aspect here, especially when combining data from patients with multiple operators that each have their data on a set of patients. So we have again this horizontally partitioned data. So this was important for the people that did this study. So we validated our approach against this data set. We used our decision trees protocol in a random forest setting because we couldn't handle 290,000 records. So instead we did this 2 to 13, like about 8,000 records. We used 200 trees, depth 4, so a fairly limited number of trees, which is actually good if you use random forest and you don't want the depth to be too large, and 11 attributes. Using this Amazon cloud, we determined that computing one tree takes about 8 minutes using 3 parties, which puts the total time at less than 28 hours, which we consider totally manageable. But note it's parallelizable. So if you have several clusters of 3 machines, then you can run it at the same time, and especially in the Amazon cloud, this is of course very easy. You can have very easy parallelization. So in the end, the total would then just take 8 minutes, basically. So these are the accuracy numbers that we obtained. Because this data set was very skewed in outcomes, there were a lot of no's and like 2% yeses. We looked at, or the initial study looked at the precision for several values of recall, and they obtained these numbers, and we obtained numbers that were only slightly worse. So then we took this as validation to see that our methods actually work, applied to large scale settings when we use this random forest approach. So to sum up, we developed this C4.5-like secure algorithm for training a decision tree based on continuous attributes. We have this initial sorting phase, and then we are limited to log n depth asymptotically per node. We reduce complexity by converting a sorting network into a permutation network. And using random forests, our protocol works on large data sets. Thank you.